Hello, in this, the last of my videos about the derivative rules, we are going to be finding rules for the derivatives of the inverse trigonometric functions, like arcsine and arctangent. So, first consider the inverse of the sine function. Some people and some textbooks write it as sine inverse of x, that is, sine with a superscript -1. Now, this does not mean that we're raising sine to the -1 power, which would give us the reciprocal of sine, which is cosecant. Instead, it means the inverse function of the sine function, the function that undoes what the sine function does. And other people and other textbooks write this as the arcsine of x. So it's just two different notations for the same concept. And in this video, I'm going to be mainly sticking with the arcsine notation. So we want to find a derivative for the arcsine of x. If y is the arcsine of x, what is the derivative of y with respect to x? Well, what it means for y to equal the arcsine of x, it means that the sine of y equals x. After all, the arcsine of x is the number or angle whose sine is the number x. But if sine of y equals x, we can differentiate both sides of that equation with respect to x. The derivative of sine of y should equal the derivative of x. Well, what is the derivative of sine of y? Remember, the chain rule is in effect, and since we are differentiating with respect to the independent variable x, the derivative of sine of something is the cosine of that thing times the derivative of that thing. So the derivative of sine of y would be cosine of y times the derivative of y, dy dx. Meanwhile, over here, the derivative of x with respect to x would just be 1. So cosine of y times dy dx equals 1. So what does dy dx itself equal? How do we solve that equation for dy dx? Well, we divide both sides by cosine of y, and we get that dy dx equals 1 over cosine of y. Now, that's not our final answer. We want our final answer in terms of x. We want to know what's the derivative of this function in terms of the variable x that it is a function of. Well, we could just say, okay, y stands for the arcsine of x, so this would make it 1 over the cosine of the arcsine of x. But I don't really want to leave it like that. That's kind of messy. We can do better than that. So remember the famous trigonometric identity that says that for any number, the sine of that number squared plus the cosine of that same number squared is always equal to 1. That's one of the so-called Pythagorean trigonometric identities. So solving that for cosine, that means that cosine squared of y would equal 1 minus sine squared of y. So cosine of y should equal the square root of 1 minus sine squared of y. And that means here where we have cosine of y, we can write it as 1 minus sine squared of y, but remember that sine of y is x, so that would be the square root of 1 minus x squared. Therefore, the derivative is 1 over the square root of 1 minus x squared. The end. Right? Or is it? You seem to be forgetting something. When we take the square root of cosine squared, we should have included a plus or minus. After all, if cosine squared equals 1 minus sine squared, cosine could either be the positive or the negative square root of 1 minus sine squared. And that would mean that the derivative should be 1 over plus or minus the square root of 1 minus x squared. But is that right? Can a derivative really have more than one value? I don't think so. So we have a problem here. We have a derivative that doesn't have just one particular value for each x. How can we fix this? But I know something you don't know, or maybe you do know it. I know some basic trigonometry. After all, consider that the sine function in general is not one-to-one, but in order for it to have an inverse, we would have to restrict the domain, that is, restrict the range of angles that we are taking the sine of so that it is one-to-one. And we do that by insisting that we're talking about angles between negative and positive pi over 2. So the arc sine of a number is not just anything whose sine is that number, because there could be more than one. Instead, it's the angle between negative and positive pi over 2 whose sine is that number. So if y is the arc sine of x, that means that not only is the sine of y equal to x, but we also insist that y has to be between negative and positive pi over 2. So you take the arc sine of something, and that something would have to be between negative and positive 1, and the arc sine of that something, by definition, comes out to be an angle between negative and positive pi over 2. But what do we know about the cosine of an angle like that? If we take the cosine of an angle that is between negative and positive pi over 2, that cosine is never going to come out negative. It is always going to be greater than or equal to 0, and that means that we don't need that plus or minus. We can dispense with the plus or minus because we know that the cosine of an angle like that is never going to come out negative. And we can safely say that, yes, the derivative dy dx is just 1 over the square root of 1 minus x squared. So that is the correct derivative of that arc sine of x function. Now notice that if we're going to be taking the square root of 1 minus x squared, the number we put in for x has to be between negative 1 and 1. If x were any bigger than 1, or any smaller than negative 1, then x squared would be bigger than 1, and the 1 minus x squared that we're trying to take the square root of would be negative. And we can't take the square root of a negative number if we're just working with real numbers. But that's okay, because if x were not between negative 1 and 1, we wouldn't have been taking the arc sine of x in the first place. Arc sine of x is only defined when x is between negative 1 and 1. The only real thing we have to watch out for is right at the ends of that interval. If x was equal to negative 1 or positive 1, then the arc sine would be defined, but this derivative would not be defined. But as long as we're strictly between negative 1 and 1, the arc sine function itself is defined, and its derivative is well defined. Okay, so that's the arc sine function. What about the inverse cosine or arc cosine function? Well, that works almost exactly the same as how we found the derivative of arc sine of x. The derivative of cosine y is negative sine y dy dx, and by working through the details, we get that the derivative of y with respect to x is, well, it turns out to be negative 1 over the square root of 1 minus x squared. So it's almost exactly the same as the derivative of the arc sine function. It just is negative instead of positive. It's negative instead of positive 1 over the square root of 1 minus x squared. Okay, what about the arctangent or inverse tangent function? What's the derivative of that? If y equals the inverse tangent of x, that would mean that the tangent of y equals x itself. So what's the derivative? Well, if we differentiate both sides of that equation, what's the derivative of the tangent of something? Well, it would be secant squared of that thing times the derivative of that thing. So here that would be secant squared of y times dy dx equals, and again the derivative with respect to x of x is 1. So solving for dy dx, we get that dy dx equals 1 over secant squared of y. Now, secant squared of y, by another one of those Pythagorean identities, is equal to tangent squared of y plus 1. So let's go ahead and replace secant squared with tangent squared. And then remember y was the arctangent of x. So really we're looking at 1 over tangent squared of the arctangent of x plus 1. Now this means whatever x is, first you take its arctangent, then you take the tangent of that, and then you square what you get. But when we took the tangent of the arctangent of x, that was just x itself. We got back x itself, and so that was what we were squaring. And so this is really just dy dx equals 1 over x squared plus 1. So that is what we get for the derivative of the arctangent function. The derivative of arctangent x is 1 over x squared plus 1. And since addition is commutative, if you wanted to write it as 1 over 1 plus x squared, that would be essentially the same thing. And this time, x can be any real number. We don't have to worry about taking a square root of a negative number. The arctangent function is defined for all x, and so is its derivative. For the arccotangent function, the derivative of that, the details of finding it are almost exactly the same, and what the derivative turns out to be is almost exactly the same. It just turns out to be negative 1 over x squared plus 1. Okay, working our way through the inverse trigonometric functions, the next one we come to is the inverse secant or arcsecant function. What's the derivative of that? Again, we start with, okay, if y is the inverse secant or arcsecant of x, that would mean that the secant of y equals x. And if we differentiate both sides of that, the derivative of secant y, well, the derivative of the secant of something is the tangent of that thing times the secant of that thing times, because of the chain rule, the derivative of that thing. So here we get tangent y times secant y times the derivative of y with respect to x. And that's equal to the derivative of x with respect to x, which was 1. So dy dx equals 1 over tangent y times secant y. Now we know what secant y is, it's x. But what about tangent y? What would that be in terms of x? Well, again, start with that Pythagorean identity that relates tangent and secant. Tangent squared y would equal secant squared y minus 1. So if that's what tangent squared is, then tangent of y should be the positive or negative square root of that, plus or minus the square root of secant squared y minus 1. And since secant y is x, that would be plus or minus the square root of x squared minus 1. So that's what we put in place of tangent y. We can put plus or minus the square root of x squared minus 1, and in place of secant y, we can put just x. Now again, we have this plus or minus that we don't want in our derivative rule. The derivative should just have one value for each specific x. So which is it? Is it the plus or is it the minus? And why? We got to be able to justify this somehow. So again, let's look at what we know about these trigonometric functions. For the secant function to have an inverse, we have to restrict its domain to one on which it's 1 to 1. That is, we can only consider the angles, well, in this case, between 0 and pi. If x is an angle between 0 and pi over 2, the secant of that angle is a number 1 or more. And if we're taking an x between pi over 2 and pi, the secant of that x is negative 1 or less. So to get an inverse of the secant function First, we only allow ourselves to take the arcsecant of a number that is either greater than 1, greater than or equal to 1, or less than or equal to negative 1. So if x is greater than or equal to 1, the arcsecant of x is the angle between 0 and pi over 2, whose secant is that number. And if x is a number that is less than or equal to negative 1, the arcsecant of that kind of a number is the angle between pi over 2 and pi, whose secant is that number. So in other words, arcsecant always gives us a result, an angle, that is between 0 and pi. But what do we know about the tangent of such an angle? Well, let's break it down into the two possibilities. If the x that we're taking the arcsecant of is greater than, I should have probably said greater than or equal to 1, then that means it's positive, and the arcsecant of that x is an angle between 0 and pi over 2, and then the tangent of an angle between 0 and pi over 2 is positive. The other possibility, if x is less than negative 1, the arcsecant of x is an angle between pi over 2 and pi, and the tangent of an angle like that is negative. Either way, secant y and tangent y have the same sign. If the secant of y is positive, the tangent of y must also be positive. And if the secant of y is negative, the tangent of y must also be negative. So they have the same sign as each other, and when we multiply them together, we're either multiplying positive times positive or negative times negative, so their product, the tangent of y times the secant of y, must be positive. Now let's go back to what we got for the derivative. 1 over the tangent of y times the secant of y. We've just shown that that must always come out to be positive. So how do we ensure that this derivative is always positive? Well, the 1's always positive. The square root, if we leave off the plus or minus and just take the square root of x squared minus 1, that's going to be the positive square root. And if we want the x part to be always positive, we need to enclose it in absolute value bars. So in order to make sure that what we get is always positive, we say that the derivative, dy dx, is 1 over the absolute value of x times the square root of x squared minus 1. So that's the rule, that's the derivative of the function arcsecant of x. And this is only defined if x is a number that is either greater than 1 or less than negative 1, which is when arcsecant of x is defined. Finally, for the function arccosecant, or the inverse cosecant of x, the details of that are almost exactly the same as finding the derivative of the arcsecant function. We just end up with a negative sign, and so the derivative of the arccosecant function is almost the same as the derivative of the arcsecant function, but with a negative sign. It's negative 1 over the absolute value of x times the square root of x squared minus 1. Now, if we put those 6 derivative rules together with the chain rule, we get general derivative rules for those 6 inverse trigonometric functions. We already said the derivative of arcsine of x was 1 over the square root of 1 minus x squared. That means that the derivative of the arcsine of anything is 1 over the square root of 1 minus that anything squared times the derivative of the anything. So this is what we get when we put those derivative rules together with the chain rule. So now let's practice some differentiation now that we have these new derivative rules to play with. What if the function that we want the derivative of is the arctangent of not just x, but x plus 3? After all, the derivative of arctangent of something is 1 over And we can write it as u squared plus 1, or 1 plus u squared, times the derivative of u. So here that would be 1 over 1 plus x plus 3 squared times the derivative of x plus 3, which would just be 1. So multiplying by 1 doesn't change anything, so we just get 1 over 1 plus x plus 3 squared. And we can either leave it like that and say, okay, that's the answer, that's what we got for the derivative, or if you like it better, we can multiply this out. If you take x plus 3 and square it, you get x squared plus 6x plus 9. X plus 3 times x plus 3 multiplied out is the x squared plus 2 times the 3 times the x plus the 3 squared. And then we can combine the 1 and the 9 and write this as 1 over x squared plus 6x plus 10. So there, and to look at that, you wouldn't think that had anything to do with trigonometric functions or inverse trigonometric functions, but that is what you get for the derivative of the function arctangent of x plus 3. Okay, what about if f of x is the arcsine of 1 minus x squared? What's the derivative of that? What's f prime of x? Well, the derivative of arcsine of anything should be 1 over the square root of 1 minus that anything squared times the derivative of that thing. So here that means we get 1 over the square root of 1 minus x squared squared times the derivative of 1 minus x squared, which would be 0 minus 2x to the first power, or just negative 2x. So I can just multiply that together and write it as negative 2x over the square root of 1 minus the quantity 1 minus x squared squared. And we can leave it like that and say, okay, that's what we got for the derivative. That's f prime of x. Or that can be simplified. First of all, we can take the 1 minus x squared, the quantity squared, and multiply it out. We get the first thing squared minus 2 times the first thing times the second thing plus the second thing squared. So that becomes 1 minus 2x squared plus x to the fourth power. And then when we take 1 minus that whole thing, the 1 minus 1 cancels out. Minus a minus is a positive 2x squared, and then we have minus x to the fourth. Now, under that square root sign, we have a common factor of x squared. So we can pull that out. We can factor this into the square root of x squared times the square root of 2 minus x squared. But the square root of x squared would be, well, it would be the absolute value of x. And there may not be any better way to write it than that. If you take x over the absolute value of x, you get positive 1 if x is positive and negative 1 if x is negative. So if, for example, we knew ahead of time that we were only going to be considering positive values of x, then we could simplify this to, we could cancel out the x's and simplify it to negative 2 over the square root of 2 minus x squared. Okay, what about if f of x is x times the arcsecant of x? Do you know what rule we're going to have to use here? The function we're differentiating is made up of two things multiplied together. That is, it's a product. So we should use the product rule. And the product rule tells us to take the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. And of course, when we take the derivative of that second thing, we're going to be taking the derivative of arcsecant x, so we need to use our rule for that. So we get the first thing, x, times the derivative of arcsecant of x, which is 1 over the absolute value of x times the square root of x squared minus 1, plus the second thing, arcsecant of x, times the derivative of the first thing, the derivative of x being 1. And we can clean that up just a little and write it as x over the absolute value of x times the square root of x squared minus 1 plus the arcsecant of x. Again, there's no real good way of simplifying x over the absolute value of x if we don't know ahead of time whether x is positive or negative. If we did, then that would reduce to either just positive 1 if we knew x was positive, or negative 1 if x was negative. But if we don't know, we may as well just leave it like that. What about if f of x is the arctangent of the natural log of x? So here, if you look at the big picture, this function is the arctangent of something. That something happens to be the ln of x. It's a composite function. We're taking the arctangent of the natural log of x. But the rule is the derivative of arctangent of anything is 1 over 1 plus the anything squared times the derivative of the anything. Here that would be 1 over 1 plus the natural log of x squared times the derivative of the natural log of x. And remember, that would just be 1 over x. So that's what we got for our derivative. You can leave it like that or multiply it together and get 1 on top over, multiplying through by x plus x times ln squared of x, the natural log of x, the quantity squared. Now what if we have the ln of the arcsine of x? This time the big picture is that this function consists of the natural logarithm of something. That something happens to be the arcsine of x, but the first thing we need is the rule for the derivative of ln of something is 1 over the something times the derivative of the something. So here we get 1 over arcsine of x times the derivative of arcsine of x. And that would be 1 over the square root of 1 minus x squared. And you can multiply that by the derivative of the x, but that would just be 1. So that's what we have for our derivative. We can multiply those two fractional expressions together, but we just get 1 on top over the arcsine of x times the square root of 1 minus x squared on the bottom.